Okay, well, welcome to today's seminar. Today, Zhuang will be talking to us about the structure of transformation groups, C-star algebra.
Thank you very much. So as a standard procedure, first I like to organize for the opportunity to give a talk. Okay, so it's anyway, it's nice to give a talk here. It's nice to be back. So I'm going to talk about some work on the structure of transformation group C-star algebras, C of X crossed by some discrete amenable group gamma, and I'm assuming that the dynamical system there is free and minimum, so that is a simple C-star algebra. But I'm not assuming dimensionality on X or anything, so this algebra might be this stable or might not be this stable. Let's just look at the structure in general, and the talk is more like a survey talk. It's going to be on something I did in the last few years. Actually, most of them before the COVID. So if some of you has heard about this talk, I apologize. So let's start. Let's look at X, compact metrizable space, and look gamma. X compact metrizable space. So it's separable. And
Gamma is discrete.
yes, it's a discrete. I only consider discrete group for this talk. It is discrete, countable discrete amenable group, and I assume that this action is free and minimal, and the why I assume this, because I really I'm in the classification of C-star algebra, so most of the time C-star algebra to me is always simple. So I look at this algebra, then this algebra is simple. Yes, I'm looking at the right action. Yes. Yeah, it's on the space it's the right action, but on the algebra it's become the left. And I'm when you compose a gamma, I just put a gamma there, not a gamma inverse. Yeah. So then this is the simple unit of C-star algebra, and also nuclear, and separable, of course, and also UCT, the universal coefficient theorem. It follows from that this gamma is amenable, and this is commutative algebra. So this is this algebra actually is a groupoid C-star algebra of amenable groupoid. So it satisfies the UCT. So those are some general properties. But let's look more properties. Let's consider some final property. Let's consider, for example, Z stability. So this algebra in general might fail to be Z stable. There are examples by Zhuang and Kerr. Based on the Wheelerson's construction, there are non-Z stable transformation group C algebras, and if it's not Z stable, what you can say about the comparison, it can fail to be strict to have a strict comparison. But then what about something like a radius of a comparison? And something more like stable rank, topological stable rank. And we will see later that this algebra actually it always has a stable rank 1, no matter this algebra is Jiangsu stable or not. So it's very much like a AH algebra with diagonal maps, like the Wheelerson algebra of the first construction. It might not be Z stable, but they are always, but they are not always that bad. So they always have stable rank 1. Let me just say here, stable rank 1, and maybe some others. Maybe others. So let's look at those final properties. And the main two I use to study those properties actually are going to be two properties of the dynamical system, or maybe this C-star dynamical system. One is a uniform version of Rochlin property, and the other one is a relative comparison property. So let's start with the uniform Rochlin property. So if you have any question, just stop me. I prepared the talk in my mind that George is here. I know he will stop me, brother.
Okay, so let's start. Empty static compact tricycle.
You got a zero algebra. Okay, zero algebra also unital, simple, UCT. They probably have all those properties. Yeah. Okay. So let's start with the uniform Rochlin property. So what is this about? Definition. So we have our space, and then we have a group action, and this is a amenable group. So X gamma decide to have uniform Rocklin property if for any compact subset of the group and any epsilon, you can find out a tower inside the space. So I draw the picture first. So maybe I just draw one tower. You can find out the tower like this is the base go to the next level, this level go to next and keep going, and the top it's just go to somewhere. So this is a tower, and the Rocklin property says that the classical Rocklin property says that you have a tower and the leftover is small under the given invariant measure. But the uniform Rocklin property, well, this is a topological dynamical system. You just say that the leftover actually is small uniformly under all the invariant probability measures. And also here, the tower, we require that it's a topological tower in the sense that the base site or the level site actually is, well, they are all open sites. Okay, so and this K and epsilon really ask that this tower is as high as you want. So if n there exists, so towers, say let's say open tower. So the base set, you might have several towers. So B1, B2. So this is going to be B, the base set. BS, those are subset of the space open, and the finite set, actually just a finite set. Say gamma 1, gamma 2, gamma S. Those finite sets take care about the translations. Such that first, say gamma S. This is a big S, capital S. Gamma S are almost invariant. Okay, epsilon invariant. In the case that this gamma is the integer group, this basically says that this this looks like a very long interval. Or maybe the union of some union of them. Two, they form a tower. You look a base set. You look a base set and then translate by the corresponding well, gamma. Then where this gamma is in this gamma S, and S from 1 to S, those are mutually disjoint. So in this picture, I only draw one tower, but you may have several towers. They should mutually disjoint. So we do not want overlaps. And 3, you look the leftover. BS gamma. No, I'm using this notation. Okay. The disjoint union of them. You look at the complement. Oh, they should be uniformly small and with respect to the invariant probability measure. So this is the definition, and in the case that you have used or seen David Kerr's almost finiteness, something like that. There are many similarities, except that here you do not assume the base side has a small diameter. So of course they have a very small measure, but they can be large, thin but large. That's one remark, and another remark is that in the case that this group is monotypeable, for example, if it's Z or ZD, then you don't need to worry about how many towers. I mean, one tower will be fine.
I think DS gamma and gamma S are mutually controlled. But you're not saying that if you take different triple gammas, the same gamma has to be controlled.
They are still, because I take all the S. Different towers, they are also disjoint. Yeah, so if you have 2, then the picture is so this is the first tower, then this is the second tower. Maybe it's only go here, but with a different shape. So this is going to be gamma 2, and the translation set here is gamma 1. But I still require that these two towers are disjoint.
Gamma S only S, but what you have here is that going to define everything number 1 to be 1.
Where?
Well, I mean, in your picture, it seems that there is a power corresponding to gamma 1, right? That you obtain, I guess, that one element to gamma 1.
Yeah, this is the tower correspond to gamma 1.
Right.
Yes.
So you're applying element to gamma 1 to be 4 and so on.
Oh.
For one road, it seems that you're applying the gamma to gamma S only to be S, for the same S.
Well, when you apply this gamma, this gamma belong to this S, and this is the same as here.
So you do one thing.
Oh yes, over here it's the same as.
Okay.
This is exactly same as. Yes. That's exactly same as. Yes. And then I allow S change after that. Yes. So that's for a given small s. That's only that's only one tower. They are disjoint. Then you look s. You look more. They should still disjoint. So yeah. But when you apply this gamma, yes, this gamma belong to this s, and that's same as this s.
I don't want the picture at all.
Sorry. Yeah, this. But in the case that the group is monotypeable, then you don't have to worry about how many towers. I mean, one is enough. You can use tiling to reduce lots of towers into a single tower.
So first condition, what do you mean by gamma S is K epsilon invariant? I mean K is gamma S.
This just means that so here we have K. This is a finite subset. So gamma S, you look the translation of gamma S. So this is a finite set. Now you translate this gamma S under the element of the given set K. Then you look at the difference of this with the original set. So this is the gamma S. Then after you translate, this becomes some other set. You look at the difference. Difference should be small. In this sense, you look at the cardinality. So this should be small. So in other words, you look at gamma S. You look at gamma S for almost all of the point. You look at the K neighborhood. It's still inside. So most of the points are inside. That's the approximate invariant. So this is the Rockling property, and
The individual pieces are exactly disjoint or just approximately disjoint?
exactly disjoint.
And would it be the same thing to say approximately?
In this case, I think so, but I never check. I think so. In the non-commutative case, I don't know, but in non-commutative case, we do look the approximate disjoint.
Yeah.
So that's the dynamical system picture. So how this related to C algebra?
Give me an example of URT.
Example. I'm going to write it here, but I'm not sure you will call it an example or something. Yeah, right. Yeah. So minimum and free and minimum. This as URP. So whenever you have a ZD action, free and minimum, it has this property.
Okay, you have an example where it doesn't hold.
No. No. Yeah.
Well, it's not minimal.
Oh, I'm assuming.
So,
Yeah.
you're
Yes.
putting
Yeah.
words into my. You're saying I'm missing some words.
Always assume free and minimum. This can be relaxed. But
If it's trivial action, then obviously not. If it's interesting, oh, that's interesting. You can relax it, you know.
yeah, slightly.
So it's not certainly not if and only. So it's not.
No.
This S that you have here, does that matter? For example, in this case, can you just take it to be one?
In this case, the group is non-tellable. So you, how many towers you can say it's always one tower. So this S is really about if you want to cover or tile the group gamma using Furner site, then how many different shapes you need. And I think this it's open problem whether our amenable group is monotileable or not.
Alpiano has a beautiful paper where he talks about actions of amenable groups, amenable discrete groups on the hyperplane 2 on Zucker. And he has a very, very original and deep analysis of tiling.
Yeah, actually, he used at that time it's quasi tilings. You don't exactly cover the whole group, but with some overlap. But now you have exact tiling. It can be improved.
Really?
Yes, yes. Yeah, we did something in the long paper.
So,
for long paper.
Just define monotileable only just so that I can.
single tile, discrete.
Yeah, it's a tiling. A tiling.
Standard definition, I just don't agree. Well, I told you.
Well, it's also that.
Monoplane means one group.
Yeah.
I mean, even the definition of tileable, I think it's more important to explain what tiling.
Yeah, this say this is a group. It can be tiled by some subset gamma 0 if you can find out some subset out of the center side, then this gamma 0, the translation there, translation there, translation there, it they are disjoint, and the union is the whole group. And in general, you may have different tiles, gamma 1, gamma 2. Then for some point you use gamma 1. For some point maybe you use gamma 2.
I think what we wanted was the definition of tileable, not monoplane. So you gave that too.
Yeah. Yes.
So gamma 1 is some non-trivial subset of the group.
It's going to be some almost invariant set. Yeah, it should be non-trivial, and it should be large. It's like you can divide Z into intervals, the long intervals. It's monotileable. You can make them to have a same length.
If you want to use it, styles are actually called reset.
Yes, yes, yes. Those those things should be as invariant as you like. Yes. And for discrete amenable group, you always can find out Furner site as invariant as you like to exactly tile the I don't know how many of them.
Finitely.
Yes, finitely many. Yes.
Is there some bound n such that for every epsilon bigger than 0, every compact set A can be n Furner sets, or maybe the number of them increases depending on what they have?
I don't know that.
Okay.
Yeah, I don't know.
So for all that's known as k gets big and epsilon goes to 0, the number of tiles you need may go to 0.
Yeah, I need to check the paper, but I don't know. Yeah, I'm not sure if there is a uniform bound or not. But yeah. So how this related to C algebras? This is the algebra of algebra. So let's look at one Rocklin tower. Let's so we have open set, and then the translation. So this open set is B0. The translation into the next by some gamma, and so on. Right here. By some gamma, by some group element of gamma. Now let's try to construct some C algebras. First, you have this open set B0. Then you have a set, you know what which is C algebra to consider. That's just let's call it B. That's just the algebra of continuous functions on this set, but it's open, so we look at the functions which vanish at infinity. Now you have those translations. You have this algebra. Those translations are given by some unitary in the cross product algebra. So you can translate this algebra to the next level. Actually, those two are isomorphic. Then and keep doing this. This really looks like those are the matrix diagonals, and the translations are some partial isometries. Then the C algebra you can look is just U gamma star. So you have some continuous functions on the base set, and then you translate using the group element from the shape. Yeah, maybe I put there. Sorry. And this unitary U is the canonical unitary in the cross product algebra. You look at the C algebra generated by those. This is a sub-C algebra of C of X crossed by gamma. And it turns out that this C algebra is very concrete. This C algebra is isomorphic. Well, you have the base set that's C0 of B0. Then the translation just give you the matrix unit. So you have this homogeneous algebra inside.
What is U gamma?
Oh, U gamma is the canonical unitary.
Okay.
Associated to
Okay,
gamma.
okay.
Yes, it's inside the cross product algebra, which generated by F and U gamma with U gamma F, U gamma star here, F composed with gamma, something like this. So those are the canonical unitary. And if you look at this guy, this gives us a very nice C algebra. This is homogeneous algebra. And exactly homogeneous, not sub-homogeneous, because they are. It's a tower. It's just a tower. So now, for each tower, you can have a sub-C algebra, and if you have two, actually you are going to have you look at this construction, you have two subsystem algebras which are homogeneous, and in that case, those are mutually mutually disjoint. Then the corresponding algebra actually they are mutually orthogonal. So suppose this is this is now the cross product algebra. You have matrix algebra here, and those sub algebras. Then by the condition 3, it almost fills the whole cross product algebra.
But in the definition here, they look at that times UR, but then your requirement to have to be quantified by UR, so you can UR f, that's by U gamma. U gamma f U gamma star is equal to f composite gamma. So you multiply f by U gamma and then by U gamma star on the right. Is there a reason for that?
Well, see, f is defined on the base side.
Yes.
You want to look at the translation. Well, if you multiply one way, you get f because it's a unitary, but let's multiply in this way. This is supposed to be some function here.
Oh, yeah.
But this, I'm not compose gamma because in this picture, gamma is gamma send this guy to that guy. So here yes, I compose with gamma inverse. So this is supposed to be something over here.
Yeah.
Yeah. Well, one way or the other, it's and so we have this algebra of a tower. Those are very nice algebra. We have a lot of them. And then on the C algebra level, what the uniform Rocklin property corresponds to? Actually, it corresponds to the Trisha approximation called the weak Trisha approximation. Weak Trisha approximation. If you work in the classification of C algebras, you know what is the Trisha approximation in the case of a lot of projections, and this is a weak version of it. Let's give a general definition. So let's pick a class of C algebras, a class of nice C algebras, something you can deal with, like a homogeneous one, subhomogeneous one, things like those. So this script S. Oh, just script S. Be a class of these algebras, and then so I only consider unit of these algebras at least for the moment. So a unit of these algebra. A is said to be weakly, trivially approximated by this class S. Let's write it as T. No, A belong to as weakly trivially S. If something like that picture happens for C algebra, so if first you have to fix the tolerance for any finite subset of A, and so this is a finite. Any epsilon, there is a subsystem algebra of A. Presumably they are going to be the well, or in this example, they are going to be the algebra of the towers. There is a subsystem algebra S in A might not be unital. In this case, S might not be unital, but A is unital. Subsystem algebra such that this subsystem algebra S is in the class S, so it's something you can handle with, something you really can do concrete computations, and some element H belong to S, and this H is some positive contraction. So this is positive, and actually has norm 1. You can require it to have norm 1, such that first, this H is almost central with respect to this given finite set F. So HF minus FH is almost 0. Two. This H, you look the cut down of H of those elements in F. Those are almost inside the algebra, the subalgebra S for all F in F. So you have something in your algebra almost commute with the given F, and then if you do the cut down, it's going to be in the tower algebra. So it's going to be inside the nice algebra, and then corresponds to property 3. It's really say that you look at 1 minus H, then it has a small trace or small rank. You can use the trace for this, but let's put a rank. So for all trace of A, so this is a weak Trisha approximation property, and now you really can compare with the uniform Rockling property. They share some similarity. So indeed we do have a theorem that to connect these two properties. One is a dynamical system property, one is a system algebra property. So theorem says that if let's just say this, if X gamma has a uniform Rockling property, this implies free and minimal. This implies that the cross product algebra is weakly trivially the direct sum of some homogeneous algebra, some ZS, some NS. So you can see that those homogeneous algebra actually correspond to the Rocklin towers. Yes.
Why is it called weakly traceably approximate if you don't use the trace? You don't use the trace.
Here is the trace.
Oh, thank you.
And
Unlike the definitions of traceally unstable that we have seen in past weeks, this actually does refer to the trace.
yeah, it's yeah, of course there is a trace, but why call it weakly traceable? This if you in von Neumann algebra, actually this approximation is really in the von Neumann algebra topology. So sometimes the traceable is small.
And the weak part is coming from what again?
The weak part, well, after this, I will tell you what is the traceable approximation. Okay. It's open. Open. It's it corresponds. Maybe I write BS. Yes. It's yeah. Those are really the base size. So those are open size. The proof actually is not really hard. It's long, but the computation is not really hard. I can tell you what this H is. This H, see, you have this Rocklin tower. Let's just say in the case that the group is the group of integers. So you have this translation and assume this is very, very tall. Then for each tower, you can have some function like this. So it's almost the support of this open set. Then you can look the translation. Maybe I use this. You can look the translation. Then look at the sum of them. So this looks like the support of the whole Rocklin tower. Of course, this guy commute with everything on X in C of X, but this guy not necessarily commute with the thing in the with the unitary. The unitary is the translation. But now you what you can do is that you for this well for the function near the boundary, this end or that end, you can push them. You can push them to 0, and next push them to somewhere very not 0, but something very small. So you can have something like some function like this. It's a tempered function, and now the translation is in this way. If you look at the translation, then it's something like this. Then it's almost the same. So roughly, yeah, you use amenability. You use that the shape is the Farner set to really make this happen. And once you have that H, you can check the cut down. It's just in there, or approximately in there. Then the rest is really the computation. It's not a short computation, but it's really the computation. Hmm? What?
No, he said that,
What is it?
he said that he's going to do the drawing for that.
Oh, he didn't do this.
I wrote it, so yes.
Next.
Yeah, Furner site. Yes, you really use that as a gamma 1, gamma 2. Those are Furner site.
No, you were saying that
Oh.
the picture, you are doing the picture for that, right? That you said at the beginning that you
Oh, yes. This for that. It's easy to draw. So maybe I to answer your question that what is the Trisha approximation? I can quickly write the definition of Trisha approximation. Then we call it the first half. So the classical definition of construction of Trisha approximation in the classification of these algebras. Trisha approximation. So still, we have a class of C-star algebras, but now let's assume everything are unital. So a class of unital C-star algebras. This class of unital C-star algebras. Then A is said trivially approximated by the algebra in S. It's usually write it as TAS script. If almost the same thing happen for any F, for any epsilon, but here for some for any positive non-zero element, there exists now a projection rather than a contraction. A projection. And some sub-C algebra of A, not a unital sub-C algebra, but the unit of S, not a necessary unital, but the unit of S actually is given by this projection. Such that then you almost have the three same conditions. First is that this PF minus FP is small for all F. Two, this the cut down. Now it's cut down by a projection. This is almost inside the sub-C algebra. And three, now we talk about this projection. It might not be the unit of A. Then we look at the leftover. We look at 1 minus P. We really require this guy is small. Not only small in trace, but its cones small for this A. So it's really small in a topological sense. So the idea of a Trisha approximation is that you can get a lot of information about the big algebra just from this nice class. So similar idea there.
And yeah, this one doesn't mention the trace at all.
That's right. That's right. Yeah, that's right. That's right. Yeah.
Require that that's in your class, not just usual homomorphism from S, which require.
Yes, here I'm using a very classical one. Yes, I'm using a sub-C algebra, and here P almost commute. Then the cut down actually give you that map approximately.
Yeah, but the map is supposed to be injected. Right, this definition saying there's an algebra S and a usual homomorphism from S to PAE. Essentially, whatever happens.
Yeah, here I'm just Yeah, I'm just assuming that S is exactly a subalgebra. Yes, yes, yes. Yeah. Yeah, maybe I stop here for the first half. So let's continue. So we have this Rocklin property on the dynamical system, and on the C-star algebra level, it corresponds to a version of Trisha approximation. And here is the classical Trisha approximation. And let's compare this classical one with this weaker one. Of course, there are some difference. First, you don't cut with a projection. So this does allow the algebra to be projectionless. Because for this Trisha approximation, you need some projection to cut. But that's not a big issue. Then you look at those three properties, you probably have well, then you probably notice that there we do have a trace, and here we don't have a trace. We say that this guy is small, actually small in the Cones semigroup. So this guy is in some sense is topologically small. And here it's only mesotheoretically small. So how to make these two property even more closer? Well, let's introduce another property to make this 1 minus h actually is even small in the Cones semigroup rather than just trivially small.
How useful is it to be just spatially small?
Not very much in the.
So whoever made this definition?
Me.
Okay, but I think this is
Yeah, well, we will make it stronger. So we will make this weak Trisha approximation stronger using another property.
There. So what if this should be changed?
You can put a trace here, then require the algebra to have a comparison. Yeah, but in general, this algebra might fail to have a global comparison. But I'm going to introduce a relative version of comparison. So relative Cones comparison. So let's look at this cross product algebra.
refer to the Cillian basis, or does it refer to no connection?
I don't know. Of course I can call this weak, but then if require this guy to be Cones small, then I don't know which should be the nice name. I call it weakly topologically Trisha or something, but it's, again it sounds kind of silly. But I cannot call it weak, strong, or.
But no, for decades almost, for a long time, people have been talking about tracial approximation to
Yeah.
mean in terms of the proximity.
Yes, yes.
So it seems to me if you're just introducing a note of confusion with it. But this, I mean, this is you want to emphasize the importance of doing it for the proximity. You don't do it right from the beginning.
No, well, because I over here I just compare to the uniform Rocklin property, and this is only small in trace. But together with the relative Cones comparison, then you really can make this.
You don't want that to be small in the Cones.
No, this is just small in the trace. Yeah.
And that's enough.
Enough for this.
Well, it's enough for proving a theorem.
Yes, but you have another property. We are going to prove theorem use two
Yeah.
properties together.
Okay, well, yes, but the final theorem will have semigroup for one approximation, but it you have trace for another.
Well,
Or-
let's look at this property first.
Well, sure.
Yeah.
But what am I thinking about it?
So we have we look at this cross product algebra. We have bigger algebra. Let's call it A, and we have canonical subalgebra, and this commutative algebra. Let's call it D. So so now we have this pair. So this pair is a Cartan pair actually. This has a relative Kunz comparison property. But I'm calling it it has Kunz comparison of open sites. So this called COS. If let's look at this subalgebra D, you have F and G, two positive continuous functions only in D, not go to matrix algebra, just in D. So there actually their Kunz class just corresponds to the open subset of X, because this is just in C of X. So we basically look at two open subsets. Look F and G there. If for any F and G, and let's look. We have two open subsets. Then we look their measure. Let's say one is smaller than another, but now the measure you are looking at really the measure of the big algebra. So you are looking at the invariant measure rather than the measure of D. So this all traces of the bigger algebra. So this should implies F is Kunz smaller than G, but not inside D. It should be inside the bigger algebra A. So this is really a relative comparison property. You are not trying to compare everything in the bigger algebra, but you only compare that subalgebra, the diagonal, and compare them inside the bigger one. And in general, you are allowed to put some multiplicities here, but for simplicity, let's ignore the multiplicity part. Now, together with this property, you really can say you really can make this guy one monoset to be Kunz small.
I'm puzzled because it seems to me that it might be quite typical that the Kunz classes of coming from D might already be arbitrary. In fact,
Well, no. In general, no. We only look at D. They are inside D. You don't look. You don't go to matrices.
well,
So you are only look at the toy semigroup.
It's not the toy one.
Oh no, only inside D.
Yes, but that's not the toy one.
The open side of X. Those are toy ones.
Yes, but well, I would almost guess that very frequently already D gave you everything.
If you allow the element from a matrix algebra of D, yes.
Well,
But here you only take them inside the D. So that's the comparison with open set.
Okay, but that's the question. This is not even a semigroup.
No.
It's
No.
certain
Yeah.
elements, so.
Yeah. Yeah.
But it's, okay, but
Yeah.
but it's, but I would guess in general, the semi-group generated by, are completely different from the void semi-group, which is already a semi-group, and it's not everything. The F and G in here, coming from D plus itself, without a matrix, their Kunz classes, well, I think one of the not surprised the semi-group they generated, and closed up on the two, was the whole
they should give you all the affine functions, but
only the toy ones do that.
this is a toy one. I mean, this generator is a toy one. You look at open size.
The toy ones are just the,
You are looking at the open size.
so thank you. Those don't, okay, first those don't generate the whole Kunz semi-group.
Yeah.
For D.
Yeah.
So,
Like about projections.
That's just a slightly different approach to what I call the toy Kunz semi-group. I've forgotten. Thank you.
Yeah.
Sorry.
Yeah, I regard them as semi-group generated by open
It's a
size.
good definition of the toy Kunz semi-group.
Okay.
It's,
Yeah.
beautiful.
But now with with that relative Kunz comparison property, you really can make 1 minus h Kunz small. So then here is then here is a theorem. So the Rocklin property plus the relative comparison property implies
That is, so that it's the relative Kunz comparison, or is it just the Kunz comparison?
the relative Kunz comparison.
Okay.
It's, you get you end up getting Kunz inequality.
No, but because you said that's Kunz comparison, you took the relative weight.
But over here it has a Kunz comparison of open size. So only restricted to the open size.
Something has come. That I was waiting for. That they were
No, but you're right. I think probably a more uniform approach, more uniform name maybe should be just a relative Kunz comparison.
Toy Kunz comparison. You can talk about
Okay.
the cases you have the toy Kunz coming just from the function that already opens that.
Yeah.
And that's that single value function. Silly, but it's still very important. And the one comparison related to that. So I think the same word toy is
Okay. So then with these two property, we can say that this C-star algebra is weakly, trivially, just somewhere over there. Weakly, trivially by the matrix algebra of BS. But with the leftover Kunz small, not just a trace small. So now it's really useful with this property, with the leftover Kunz small. So this can be regarded as a structure theorem for the cross product algebra, and by the way, we have properties, but when the property holds, like example, this has this property, and at the same time, it also has the relative Combs comparison property. So for ZD, it's really nice. You have well, arbitrary minimum and free actions. They have both properties. For other groups, you have some partial result, like this. So with first, assume it has a Cantor factor.
You put them together, URP plus COS, they go together, because the COS implies with the URP, it is good at the same, it does imply a good small.
Yeah, Combs small follows from this. Yes.
So look, I'm saying that if you look at the URP, then that doesn't, the URP does not require a priori all by itself. It doesn't, it just talks about traces.
Yes.
But
Yes.
yeah, but what I'm noticing, it seems to me, is that if you combine it with COS, then the trace condition becomes the small.
Yes, that's here. Yes. Yeah, that's kind of the purpose.
Well, that's not a theorem, that's a triviality. So that's
Okay.
COS, you assume COS and URP, then this follows within the URP that the condition 3 does hold with
Yeah. Okay. Let's.
That's not part of the theorem.
No. Okay. Remark.
Oh, yeah. But that's why I thought it was your big theorem.
Yeah, this is combined with the previous theorem together.
Still be coming up tomorrow.
Yeah, maybe I can say this. The relative comparison guarantee you that the leftover is Combs small.
So what's WT?
Weakly trivially.
Well, but that direct sum is a logical direct sum.
Yeah, it's the thing from the tower. Yes.
Oh, how we just add? Fun.
Yeah.
No, but what does weakly expect to be direct sum?
Oh, sorry. Weakly trivially approximated by algebra like this.
Right.
Yeah. So.
In the definition, you somehow something related to a strict comparison. Add R, what do you expect to see here?
Adding R.
Yeah, because the theta of F plus R less than theta of G implies F is also different.
You want a gap? You want a gap here. You want some gap.
So therefore,
then you don't have this. You cannot say the thing with small trace is really small or not. Yeah, you certainly are allowed to make some multiplicities, but adding a gap does not imply the thing with small trace is Combs small.
Well, I suppose that what one expects is a fairly generally this toy what's generated in the category by D plus and D plus is going to be equivalent to the outside function. And a non-compact element will just be the outside function point-wise away. Isn't that the what is nominal, what is, I think it's-
Well, we cannot. This cannot get to something we talked yesterday. It's cannot.
I don't know. You're just saying we don't know that yet.
No.
No, but it's,
No.
that's just, that's not saying it doesn't, that's not saying it, that's not saying that it's not reasonable to look forward.
Yeah, we can.
Only typically, this is going to be, you know, I think it's a little, I think it is a little incomplete just to look at B plus, because that's not a, I mean, it doesn't fit in the Kunz category. What you want is to look at the sub-Kunz semigroup generated by the D plus. You want the whole Kunz category up. You want to take account of the fact that this is a sub-object of the Kunz semigroup of the community development.
Well, I guess that's what you get if you allow multiplicities.
Sorry?
I guess that's what you get if you allow multiplicities.
I'm not quite sure what you mean by multiplicity.
Yeah, okay, so I think that, I mean, you mentioned that,
Well-
the statement is you have, say,
Well, you just look at the sub-Kunz object generated by the.
yeah, you have some integer positive integer multiple of F. And it's second level is some other positive integer multiple of G, and the corresponding to that sum.
That's certainly that's the whole, the strict comparison, the whole, everything in the whole point from something. But in fact, since it is, if you look at the non-compact elements, then you expect it to be just less than or equal to the vector equation. It's the same as less than or equal to in the Kunz but so you're not, that's not an axiom, but one expects, I think one should expect it to consequence of the axiom. Well, and I think in the meantime, it's slightly artificial just to look at the open sets. You want to look at that you should take advantage of the fact that discovered by Edouard and me that well, wasn't aware that he had done it. You say an arbitrary committed to secret algebra, same with unit, and you look at the Kunz semigroup, then you look at the infinite sums of, you look at the sub object generated by the open sets, which will be the sigma compact the one in the separable case. You look at all the open sets, and those are in the Kunz semigroup, and you look at what they generate as a sub object, and it turns out it's exactly a sub object. That should become part of the technical apparatus.
Yeah, to show this, actually, the argument does what the argument was to reduce to either matrix algebras or over some C of B, or maybe to some subhomogeneous algebras.
I think it's misleading to talk about matrix algebra because it's only the sums of things from the commutative algebra that you're talking about, not things.
No, not matrix algebra over D. No, but D, a part of D will be the diagonal of some other matrix algebra, like from the Rocklin towers. So no, not to the matrix algebra of D, but to the matrix. So this thing is D, but to a matrix algebra of this guy. So that's more or less. Yes.
On the basis of what that was I've been looking at, what you want to be looking at is a whole Kunz sub-object, a whole Kunz category sub-object of the Kunz semigroup of P of F. It actually is a sub-object. It's posed on a compact containment and it's mapped exactly the way and so on. So, and it can be described exactly as this lower semi-continuous integer value
Well, this was a formulation 6 years ago. something
Well,
like
okay, but, 9
I
months
think
ago.
it's 6, yeah, about 6 years. So actually those property holds for all ZD action and also for some other groups there are some partial result, and also by Kerr, Gabazaba and Kerr, that if for arbitrary if this system has a small boundary property, then they oh no, I take back on this. They have a Rockling property, but for these two, they have a Rockling property plus the relative comparison property.
So
Yeah.
you could relax minimal.
Hmm?
So you can relax minimal.
Oh yes, for maybe also for this, I never check, but for this, minimality can be replaced by marker property. Marker.
Both European field, both of the properties.
Yes.
Are you saying Markov?
Marker. Markers property or marker property. Markers property.
Yeah, Markov you have for any free action of finite dimension. So I think that's
Which?
I think for any free action on a finite dimensional space, you have Markov. So there's a company example for it.
There are examples which without markers property. I don't know. I didn't. I only know there are examples, but I don't know that.
Sorry, what you say is example and empirical.
There are examples, free action, but without markers property.
Yeah, but you were also saying that an example and empirical.
They showed that if you have a system with a small boundary property, then you have the Rockling property. And actually over there, you can make the diameter of the level set to be arbitrarily small, so it's almost finiteness in measure. So what's the application of these two properties, or what's the application of this structure theorem? So maybe I just summarize the theorem and explains. Applications of URP CUS. So theorem. So first, so assume free and minimal. First is that it's a generalization of a theorem with George. So if the dynamical system has a mean dimension 0, that's a dynamical version of dimension growth, and this condition holds if x.
Okay, good.
This property holds if the mean dimension holds if x is finite dimensional, or if there are finitely many accountably at most accountably many algorithmic measures of finite topological entropy. So whenever mean dimension is 0, then I just use A as the cross product algebra. Then this is Z stable. So
is your back.
A is this. A is the cross product algebra. Yes. So maybe right here. Let's say A is C of X crossed by gamma. 2.
Without any conditions on gamma.
No condition on gamma. Just assume these two properties. Yeah. Yes, assume.
Okay,
Yes, yes, these two properties. 2 is that in the case that A is not this stable, then you can talk about the radius of comparison. So the gap, something like that. There exists that suppose there exists a gap so that this implication holds. You want the smallest gap so that holds. That's called the radius of comparison of A, and it can be controlled by the mean dimension of the system. And
you are here the CO.
yes.
So you think this does not imply speed comparison?
No, of course not. This system, they always have these two properties. But you have cross product from there, which is not this stable.
Does almost the finite imply speed comparison?
You mean in measure? Or?
Well, plus some comparison, like CO.
Well, then of course it implies. Because in the picture of Trisha approximations, well, I will explain in a moment. It's really like the algebra is weakly Trishally approximated by finite dimensional, or maybe you can dimension drop algebras. Yes.
Table right one.
I will write.
Okay.
A moment.
I like the theory.
A stable rank is always 1, no matter the algebra is classifiable or not.
That's what my question is.
Yes.
Assuming URP plus.
Yes. Maybe.
You got two together.
Yeah, two of them together. Maybe theorem. This. Assume this.
Okay, but then this consumer group, as we've been discussing, this consumer group is really related to what you're talking about. I mean,
It should be.
because there is
Yeah.
the Thiel and Company semi-group.
Yeah. Yes.
Then you have table right one, and you have there's a copy of the outline function sitting inside the semi-group.
Yes.
And so basically, the COS essentially says that come in. It's not 4 o'clock yet. We can. Not 4 o'clock. Okay, so the sort of culmination of this COS is the toy image of the toy semi group is just the outline function. You don't want to put that in the axiom because it's too strong. So it's probably concept. I'm sure you're concentrating.
Yeah, but actually, probably you really mean something strong, not just the image. Also the order. The order is somehow.
Well,
yeah.
The image has a
Yeah, because of this comparison thing. Yes.
Well, the image has a subset of the consuming.
Yes. Yeah.
It's just the outline.
Yeah. Also, the order is determined by.
Of course.
Yes.
Yeah, well, I guess I should be happier to get words put in there.
Well, so this algebra. So when it's Jiangsu stable. This happened if and only if radius of comparison is 0. So if and only if it has a strict comparison on positive element. So in particular, this says that the full version of Tom-Winter conjecture holds for the cross product algebra, assuming these two properties. Okay, assuming those two properties. And by the way, these two properties really should hold beyond the case. It really should be true in some general context. And so
what types of groups do you think of, like, those should be true for amenable groups, or like?
yeah, amenable, yes, amenable. So those four 1, 2, 3, 4 are kind of has been a while, and then here is a 5. This is something I talked about in the in early July, and it's it say that if trace of A is Bauer, then A has to be this stable. So in other words, if you look the non-Z stable, so the singular transformation group algebras, the trace simplex has to be not so nice.
Okay, but this is just for a substitute for saying not full. It's a partial result. I mean,
yeah.
The only there are no examples whatsoever. If it's not power, then it's not full.
Yeah, there might be some well, but yeah, in some context, yes. The Poisson simplex. If you look at the non-Z stable one, the Poisson simplex always happen somewhere.
I don't quite understand. I'm just saying that the corrected version of 5 would be the final version of 5 would be anticipated would be the TA is not.
Well, yeah, but here is some construction of Elon and Chris. They can construct some C algebra like looks like a Wheelerson algebra. So it's not this stable. It's a gluing of two Wheelerson algebras. It's more or less the direct sum of two Wheelerson algebras. It's not that stable, but now you look at the trace. The trace simplex is a Poisson simplex, another Poisson simplex, then the span of them. So the whole thing is not Poisson, but the Poisson is still there.
Well, so it's not quite A plus A. It's some simple.
Yeah, with some the trace simplex is exactly same as that.
Is it even meaningful? Is it meaningful?
Yes.
It's an AH algebra.
Yeah, A is the Wheelerson algebra, or the column part of the Wheelerson algebra.
It's a simple unital algebra.
Yeah.
Does it have stable rank 1?
Yes, it's an AH algebra with diagonal map.
Sorry?
It's an AH algebra with a diagonal map. So yes,
Well,
that's stable rank 1.
Then what I suggested is not.
Well, but see, the Poisson simplex is still there. It's just the whole thing is not Poisson simplex, but one endpoint or the other endpoint is still the Poisson simplex.
Well, you mean that there's a face, and the face which is the full.
Yes.
Okay, well then that's maybe that's what we have to tell for. There's some.
Yeah. So maybe I say something about the proof. The proof go to the Trisha approximation picture. So this is our cross product algebra. The Trisha approximation picture says that you can have some subsystem algebra which almost fill the whole algebra, and this algebra is homogeneous. Let's just say Mn over C of C0 of B. For the mean dimension case, turns out that you can make this homogeneous algebra better. You can even find a sub algebra there. You can choose some C0 of let's call it Z in this case, so that the dimension, the topological dimension of Z compared to the matrix size, this is dominated by the mean dimension. Well, roughly speaking, it's like that. Then you can play the comparison. You play the card, then the comparison. You do it inside this homogeneous subalgebra. That's more or less you get this and get this, and for stable rank 1, you can well, you have matrix algebra, then you have a diagonal, and on that diagonal, well, very roughly speaking, you can write everything as diagonals, and then you can have some room to play. It's from the Rocklin towers. So. And it turns out that this argument for the stable rank 1 case, actually it's not only works for cross product algebra, that it again works for H algebra with diagonal maps, and even for Z stable algebras, because in the Z stable algebra there is a diagonal, just a tensor with Z. You write A as A tensor Z, then you have A tensor Z tensor identity. It's a diagonal. So
You're saying it gives a new proof of the known result.
Yes. Yes. And this and for 4 you again you use this picture because now the algebra is trivially approximated by something which is locally finite nuclear dimension. Then you assume strict comparison. You can compute the Kunz semigroup. Then you use Winter's argument. You get that the algebra is trivially Z stable, and since the algebra is nuclear, then the algebra itself is Z stable. And for 5, again you use this Rocklin tower. You can find out some trace cutting central element inside D, inside the Cartan subalgebra. Then you can prove the dynamical system there must have a small boundary properties, and then by 1 it has to be this stable. So I stop here. Thank you very much.
Take this